Who spilled sand on my workbench? Wait a minute. That's not sand.
Thing, like Tesla.
This is Geek Thoughts Micah. The show is Think Like Tesla. So yeah, not actually sand, but tiny little resistor arrays. And why? We'll get to that in just a second. So over the next couple weeks, I want to work on a project with you guys. So there's a convention coming up called FogCon in about 8 weeks as I record this. And I want to have a cool little name badge. So on special, so when you build a project, you need to have a good idea of what you're building to start with, at least normally. So on special, I got some LED segments, 16 segment. So you're probably used to 8 segment, the kinds of things you see on microwaves or alarm clocks. But if you've played pinball, or you've probably seen something like this, these 16 segment displays, there's a lot more flexibility in what you can show off. You can do uppercase and lowercase, you can do special effects, you can do animations, you can do all kinds of cool stuff. So I got these for 99 cents each, and each one has 2 characters in it. I have 4 of them in total, even if you can't see them all here. Okay, so let's look at the data sheet for these and see what we have to do. All right, a bunch of physical specifications. Now notice the interesting layout here, just for when we get to figuring out the fonts. The top segment is not evenly split like a lot of 16 segments. It's got this one little corner piece. So maybe there's something cool we can do with that. Here's the internal diagram. This is called common anode. So all the 16 segments and a decimal point, so there's actually 17, are all tied together here. And then the anodes for character 1 and character 2 are also brought out separately. So we have to pick character 1 or character 2, which one we're displaying at a time. If we're showing different things on character 1 versus character 2, we have to switch back and forth quickly, something called multiplexing. Well, let's talk about that in just a second. But the other thing that wasn't super apparent when I bought it, but it's right here in the datasheet, is the spacing here between pins is very small. Normal IC spacing would be 1/10 of an inch or 2.54 millimeters. This is half of that, 1.27 millimeters between pins. So it's double spaced. So that means I can't just stick this thing into a standard breadboard. This is going to make this project a little bit more interesting. All right, multiplexing. So I'll include a link to this website below. But the basic concept is if you have rows and columns, by switching on a row at a time, say you can then decide which elements in that row are you going to display. So one at a time, you cycle through displaying things in each row. And if you do that quickly enough, regular human eyesight can't tell the difference. It looks like it's lit up. Now, I don't know if this is just me or if it's everybody, but if I turn my head to the side really quickly, or if I just move my eyes quickly, I can actually see the individual blinks. I've always seen this in alarm clocks and even more recently on automobile headlights and stuff. So we're going to have to multiplex these 16 segments. Now we've got 16 segments, we've got 8 characters, 16 times 8, 32, 64, 128 individual data lines we need to control. Well, that's going to be a little bit of a problem. So I'm thinking this is going to be driven off of an Arduino, probably an Arduino Nano. And that has, if I recall, you can configure it for up to 14 output pins. So that's not even enough for one character. So we need to do something else to make this work. This is where shift registers come in. Now, a shift register is, in particular, we're talking about a serial in, parallel out shift register. So this lets us send in the data 1 bit at a time, and it stores up little bits of data, and then when we tell it to, it sets all the outputs to the value that we just sent in 1 bit at a time. Does that make sense? Well, let's look at the logic table here. This will tell us everything we really need to know. Okay, so the bar over the top means it's inverted. X means don't care. So we don't care. If OE is high, all the outputs are disabled. Now there's outputs A through H, so that's 8 bits on this one. If OE is inverted is low, that means it's enabled. Okay, that's everything we need to know about OE. Shift register is cleared. All right, so shift register clear, inverted line here. If that's low, bringing that low is going to clear off our shift register. Okay, so shift register is where we accumulate one bit at a time as we're feeding it in. There's also separately a storage register. That's what actually is presented on the output. So the cool thing about this chip is those two are separate. So we can be displaying one thing, it's locked in, latched in on the storage output register. And then while that's locked in and still just showing one thing, we can get the next thing that's going to show ready in the background, feeding it in one bit at a time. Once it's all ready, boom, we send it over. And that's what this is showing. So we present the data on the SEER line, serial input, either low or high. And this is a positive leading edge. As it goes from low to high, as it flips over, either the low bit or the high bit is stored in the shift register. And then our clock, this is the output register. When this goes from low to high, the shift register data is stored in the storage register. So that's cool. That gets us 8 bits. We still would need 3 input lines from our microprocessor, right? So we'd have to drive one to drive the serial input, one to drive the serial clock, and one to drive the output register clock, I guess. So that's okay, I guess. Doesn't get us very far, but here's the really cool thing. Not only is there outputs QA through QH, there's another output on this called QH prime. So when you fed in all 8 bits of the register, there's actually a 9th bit that will show up here. It doesn't present on the storage register, but it does present on an overflow pin. So you can pipe that the overflow pin over to another one of these, so you can stack these things. You can daisy chain them together, and you can make a shift register as long as you want. So that sounds like the ticket for what we need. Okay, let's take a quick look at what this might look like in the schematic diagram. And for this, I have used KiCad. KiCad is, if you're used to Mac, if you're expecting this to be like a Visio or one of these Mac graphic applications, you're going to be in for a surprise. It's very tuned for certain things and doing lots of things in quick sequence. So a quick look at this schematic here. These 2 boxes here are our shift registers that we just talked about. Here we can see the 8 outputs, and here's that overflow output. And notice that it's flowing right in to this next shift register for 8 more outputs. So this is a total of 16 bits on this line here. This is a bus line, so it's, instead of having to draw 16 wires, we just drew 1. Okay, the data, latch, and clock are just presented externally. So this board is meant as more of a peripheral. The Arduino or Raspberry Pi or whatever kind of microprocessor you want to hook up is separate. Okay, here's the serial input. And there, notice latch and clock are tied to both of these. We have some decoupling capacitors just to prevent any weird stuff from happening. And these guys here are resistor networks. 8 resistors in a row, specifying 100 ohms for this one, 470 for this one. So in this configuration, what would happen is our Arduino loads up the 16 bits for 1 character's worth of display. Now there's a total of 8 different transistors here. So this is going to require also 8 more lines, digit selectors from our microprocessor. And one at a time, we light up 1 digit from here. This shows 1, but there's actually 2 in this unit here, right? Character 1, character 2. So we step through all 8 characters one at a time. And for each one, right before we turn it on, we load up in serial fashion the 16 bits of the digits to enable the displays. So that makes sense. Now, one problem with this is each of these characters, of our 8 characters, is only lit up 1/8 of the time. So that might look very flickery. I don't know how good it's going to look. And I'm kind of hard-pressed to breadboard this before I put it together, or maybe have a circuit board built. So that's a kind of a conundrum. If you guys have any thoughts, I'd love to hear what you think. But what I will probably do is, if having 2 of these 74HC595 lets us light up only 1/8 at a time, we can increase that. Right? We could increase. This gives us 16 outputs. If we have 2, 4, 6, 8 of these, so now we have a daisy chain going out the full 128 bits. Now we can display half of the digits at a time. For instance, we could show we'd only need 2 of these transistors, right? We'd only need 2 lines here for digit select. Even or odd basically is what it would be. So we could display all the even digits in one cycle, and then all the odd digits, characters, whatever, in the next cycle. So now they'd be lit up 50% of the time, which is probably better than most alarm clocks, probably better than most VCRs, good brightness. The component count gets a little high, but what the heck? This is a project. It'll make it fun to lay out on a printed circuit board. Okay, so in the weeks to come, here's what we're going to do. We're going to refine this design in the schematic. We're going to get it just the way we want it. Then we're going to lay it out on a circuit board, and then we're going to send the circuit board off to get sent back to us as a physical object. We'll solder it up, and we will see what happens. This is going to be fun, all right? So if you guys have any thoughts, any comments, any suggestions, let me know, and we will get to this. All right. Take care, guys.